The Heisenberg Uncertainty Relation. The wave packet constructed in the previous sections obviously has properties that are reminiscent of a particle, but it is not entirely particle-like. The wave function is non-zero over a region in space of size 2 delta x. In the absence of any better way of relating the wave function to the position of the atom, it is intuitively appealing to suppose that where psi into x comma t, which is a wave function, has its greatest amplitude, is where the particle is most likely to be found. That is, the particle is to be found somewhere in a region of size 2 delta x. More than that, however, we have seen that to construct this wave packet, harmonic waves having k values in the range k bar minus delta k, comma k bar plus delta k. So this is an interval where the harmonic waves having k values were adding together. These ranges delta x and delta k are related by the bandwidth theorem, which applies when adding together harmonic waves, which tells us that delta x delta k is greater than or equal to 1, and when we will use p is equal to h cut k, we have delta p is equal to h cut delta k, and after putting this value we will get delta x delta p, which is greater than or equal to approximately equal to h cut. Okay, a closer look at this result is warranted. A wave packet that has a significant amplitude within a region of size 2 delta x was constructed from harmonic wave functions, which represent a range of momentum in the interval p bar minus delta p to p bar plus delta p. We can say that the particle is likely to be found somewhere in the region 2 delta x, and given that wave function representing a range of possible momentum were used to form this wave packet, we could also say that the momentum of the particle will have a value in the range p bar minus delta p to p bar plus delta p square. The quantities delta x and delta p are known as uncertainties, and this relation, as you are seeing on the screen, this relation is known as the Heisenberg Uncertainty Relation for position and momentum. All this is rather abstract. We do not actually see a wave function accompanying its particle. So how are we to know how wide the wave packet is, and hence what the uncertainty in position and momentum might be for a given particle? Say an electron orbiting in an atomic nucleus, or the nucleus itself, or an electron in a metal. Or the answer to this question is intimately linked with what has been suggested by the use above of such phrases as where the particle is most likely to be found, and so on. Words that are hitting at the fundamental role of randomness as an intrinsic property of quantum system and role of probability in providing a meaning for the wave function. This is an example, and this example is related to Heisenberg Uncertainty Principle. Let me explain this example. An electron is confined to a region of width 5.0 multiplied by 10 raised to the power minus 11 meter, which is its uncertainty in position delta x. Estimate the minimum uncertainty in its momentum. Simply, you will apply the Heisenberg Uncertainty Principle delta x and delta px, which is always greater than or equal to h. So here we actually want to find delta px. So it will be delta px is greater than or equal to h over delta x. So what is the value of h, which is a Planck constant? It is 6.626 multiplied by 10 raised to minus 34 joule second, and the other value is given, which is delta x width, region width, which is 5 multiplied by 10 raised to minus 11 meter. After dividing it, we will get the simple answer, which is 1.33 multiplied by 10 raised to minus 23 kilogram meter per second. It's okay. So to get a flavor of what is meant here, again we are discussing about the Heisenberg Uncertainty Principle. We can suppose that we have a truly vast number of identical particles, say 10 raised to the power 25, all prepared one at a time in some experiment so that they all have associated with them the same wave packet. For half these particles, we measure their position at the same time, that is, at say 10 seconds after they emerge from the apparatus. And for the other half, we measure their momentum. What we find is that the result for the position are not all the same. They are spread out randomly around some average value, and the range over which they are spread is most conventionally measured by the usual tools of statistics, the standard deviation. This standard deviation in position turns out to be just the uncertainty delta x we introduced above in a non-rigorous manner. Similarly, the results for the measurement of momentum for the other half are randomly scattered around some average value, and the spread around the average is given by the standard deviations once again. These standard deviations in momentum we identify with the uncertainty delta p introduced just like s. With uncertainties defined as standard deviations of random results, it is impossible to give a more precise statement of the uncertainty relation, which is delta x delta p is greater than or equal to 1 over 2 h cut. But we will mostly use the previous equations that we have described in the last slide. The detailed analysis is left to much later. We will also discuss a little detailed descriptions of this, I means delta x delta p, which is greater than or equal to h cut, in the next lectures. Okay, the more theoretical descriptions of Heisenberg Uncertainty Principle is that the Heisenberg relations has an immediate interpretation. Okay, what kind of interpretations it have? It tells us that we cannot determine from knowledge of the wave functions alone the exact position and momentum of a particle at the same time. In the extreme case that delta x is equal to 0, then the position uncertainty is 0. The last equations tells us that the uncertainty on the momentum is infinite, delta x delta p, which is greater than 1 over 2 h cut. These equations tells us that the uncertainty on the momentum is infinite, that is, the momentum is entirely unknown. A similar statement applies if delta p is equal to 0. In fact, this last possibility is the case for the example of a single harmonic wave function considered, that we consider in the previous sections where we study the wave functions, which is psi into x comma t. However, the uncertainty relations does not say that we cannot measure the position and momentum at the same time. We certainly can, of course we can measure, but maybe there is some other difficulties to find the positions and momentum of the particle. But we have to live with the fact that each time we repeat this simultaneous measurement of position and momentum on a collection of electrons, all prepared such a way to be associated with the same wave packet. The results that are obtained will vary randomly from one measurement to the next. That is, the measurement results continue to carry with. This is uncertainty by virtue of the uncertainty relation. This conclusion that it is impossible for a particle to have zero uncertainty in both position and momentum at the same time flies in the face of our institution. Namely, our belief that a particle moving through space will at any instant have definite position and momentum which we can in principle measure to arbitrary accuracy. We could then feel quite justified in arguing that our wave function idea is all very interesting, but that it is not a valid description of the physical world, or perhaps it is perfectly fine concept, but that it is incomplete. But there is information missing from the wave function. Perhaps there is a prescription still to be found that will enable us to complete the picture, retain the wave functions, but add something further that will not forbid our being able to measure the position and momentum of the particle precisely and at the same time. This of course amounts to saying that the wave functions by itself does not give complete information on the state of the particle. Einstein fought vigorously for this position, that is, that the wave functions was not a complete description of reality, and that there was something, in some sense, a responsibility of missing informations that will remove the incompleteness of the wave function, so-called hidden variables. Unfortunately for those who hold to this point, evidence has mounted, particularly in the past few decades, that the wave functions or its analogous in the more general formulation of quantum mechanics does indeed represents the full picture. The most that can ever be known about a particle, or more generally any system, is what can be learned from its wave function. This means that the difficulty encountered above concerning not being able to pinpoint the position and momentum of a particle from knowledge of its wave function is not a reflection of any inadequacy on the part of experimentalists trying to measure these quantities, but is an irreducible property of the natural world. Nevertheless, at the microscopic level, the uncertainties mentioned above become so small as to experimentally unmeasurable. So at this level, the uncertainty relation has no apparent effect. The limitations implied by the uncertainty relations as compared to classical physics may give the impression that something has been lost, that nature has prevented us to an extent quantified by the uncertainty principle from having complete information about the physical world. To someone wedded to the classical deterministic view of the physical world, and Einstein would have to be counted as one such person. It appears to be the case that there is information that is hidden from us. This may then be seen as a cause for concern because it implies that we cannot even in principle make exact predictions about the behavior of any physical system. However, the view can be taken that the opposite is true, that the uncertainty principle is an indicator of greater freedom. In a sense, the uncertainty relations means it is possible for a physical system to have a much broader range of possible physical properties consistent with the small amount of information that is available about its properties. This leads to greater richness in the properties of the physical world, than could ever be found with classical physics.